So even though we call this phyllosilicate chemistry, technically we're going to start out with our things that are not silicates. So we're going to look at brucite, which is usually written as MgOH2, but we're going to take 3 times the amount. We'll take this recipe for the mineral brucite, but we'll multiply it by 3. So we have Mg3OH6. And the reason we do that is so we can use this clever little technique that is shown in the textbook by Klein and Dutro to illustrate the structure of brucite, which can be written as Mg3 and then OH3 on top, and then a little fraction sign, and then OH3 on the bottom. This is not really a fraction. This is really meant to indicate structure. So if you remember our diagram of these octahedral layers, we had a bunch of octahedra that were connected like this. We had a layer of OH at the top, a layer of OH at the bottom, and a bunch of magnesium or aluminum atoms for the case of gibbsite in between. So we had an OH and then a magnesium and then an OH layer. So we're just showing that here. This is a layer of OH, and another layer of OH, and then a bunch of magnesiums that are sandwiched in between. So that's really just this formula. I see a mistake there. That should be an OH6. This is this stuff just rewritten like that. So the reason we're showing it this way is that we can create a TO structure by taking 2 of those hydroxyls and substituting Si2O5. We call it Si2O5. It has a 2- charge. Each hydroxyl has a -1 charge. So if we pull out 2 of the hydroxyls, we can put in 1 of the Si2O5 units. And these are the tetrahedral layers that we illustrated in the earlier video. So if we did that, then we would have something that looks like this. So we'll do Si2O5, we'll put him on the top layer, and if we've taken out 2 of the hydroxyls, we have 1 left, so there's an OH there that's left on top. And then we have 3 hydroxyls on the bottom. If we rewrite that in a more standard notation, then we would have Mg3, Si2O5, and we have 4 hydroxyls total, and that would be the formula for a mineral called lizardite. And this is the start of at least one kind of TO structure. So we have a tetrahedral layer up here, and then we have an octahedral layer down here represented by the magnesium atoms that are bonded to those hydroxyl units. So that's our TO and these little doublets. We'd have a TO package and then some van der Waals bonds that would connect the next TO package, and then some van der Waals bonds, and the next TO package. And those little doublets would go on ad infinitum. Let's erase the chalkboard and look at 2 more examples, or really 1 more example. We're going to start with the mineral gibbsite, and that is very similar to brucite, except, well, let's take the brucite formula. If we have 3 magnesiums and 6 hydroxyls, the magnesiums have a 2+ charge. There's a total of 6+ cations filling up those octahedral sites here. For gibbsite, we're going to put in aluminum, but with aluminum having a 3+ charge, we only need 2 of them to balance the negative charge on those 6 hydroxyl sites. So we have the formula Al2OH6, and we can play the same game we had before. So we can write Al2 and then OH3 on top and OH3 on the bottom. But we could take out 2 of those hydroxyls and put in an Si2O5 unit. And if we do that, then we would have Al2 with an Si2O5 in that top layer, leaving 1 hydroxyl left, and then we would still have 3 hydroxyls on the bottom. If we rewrite that in standard format, we'd have Al2, Si2O5, OH4, and that would be the formula for kaolinite. So kaolinite is another one of these TO-type structures where we have a tetrahedral layer here, and then an octahedral layer down here, and those TO layers would just repeat over and over and over again, bonded to one another by weak van der Waals bonds. And we'll just end by showing a little bit of terminology. We've talked about minerals that have either 2 aluminums or 3 magnesiums per formula unit. And we might have just a series of hydroxyls, or for the case of gibbsite over here or brucite down here. We can rewrite the mineral formula we were just looking at, Si2O5 and then OH4 for the case of kaolinite, and then Si2O5, OH4 for the case of lizardite, where we have magnesium filling those octahedral sites. If all of the octahedral sites are filled as they would be with magnesium, then we have layered silicates that are referred to as trioctahedral. On the other hand, if 1/3 of those sites are empty, and we could put a little box here to show a vacancy, right, we would have 3 magnesiums. You could think of this, let's just put 3 empty boxes. Then we could write Si2O5, OH4 for the case where we put a magnesium here and a magnesium here and a magnesium here. That is on this 5-oxygen basis with 4 hydroxyls, that would be trioctahedral. We're filling up all the octahedral sites with magnesium atoms. On the other hand, if we are going to take those 3 octahedral sites and only fill in 2 of them, let's say with aluminum, let's say we'll put aluminum in that one and aluminum in that one and leave this guy empty, then we would have something that is dioctahedral. So we have this terminology that we use for layered silicates. Things that are dioctahedral have 2 atoms per 3 octahedral sites per 3 sites that are being filled. And then for the trioctahedral case, all 3 of the octahedral sites are being filled.